say a few more things about non-context-free languages, and that'll do it for our discussion of context-free languages and the pumping and all that business. I have really 3 more examples. The first is very similar to the ones we did last time, just to get us warmed up. How about, okay. I'm talking about something like this: a to the n, c, b to the n, a squared, c to the n. This is not context-free. Not a context-free language. All right, let's see if you can remember how you do this. We use the pumping lemma for context-free languages, which is about pumping parse trees. So the proof is always by contradiction. So I begin by saying, for the sake of a contradiction, we assume that it is, I'll call it L. We assume L is a context-free language. So L. Oh, all right, thanks. Are they saying that in the chat? Yeah, it is. I'm on mute. Sorry about that, folks. Somebody noticed. Thank you. Can you hear me now? Yeah, probably. All right, I'm assuming that you can hear me now. Okay, so we assume, yep, all right, thank you. We assume that this is a context-free language, so that means L has a string UVWXY is how I usually write this. I suppose you can write the letters however you want, but it has a string UVWXY in L with a pumping parse tree. And so that means that UV to the I, WX to the I, Y is also in L for all I. All right? And from here is where we derive our contradiction. So you have to consider this word, this string UVWXY is in L. And also UV, now I said for all, those are I's and for all I, but really it's typically only necessary to use I squared. So I'm just going to write UVWXY is in L. And also UV squared, WX squared, Y is in L. All right? And when you look at the format of the string, this is what it means to be in L. It has to have this format. A bunch of A's followed by one C, followed by a bunch of B's, followed by 2 A's, followed by a bunch of C's. The only way that this could fit in that format, UV, WXY, and also have UV squared, WX squared, Y, is also of that same format. The V and the X, they have to be parts of these parts which have the nth power on them. Otherwise, when you square them, it'll break the format, right? If, for instance, if the V was like just this C, when you square it, it'll mess up the format. Or if it had one of these A's together with this C, that messes it up. So the V and the X, so the V and the X are substrings of the A to the N or B to the N or C to the N parts, right? In particular, they don't have any mixture of letters inside them. The V and the X, they got to be all A's or all B's or all C's, all right? They have no mixture of letters, right? Those V's and the X's, they must be either all A's or all B's or all C's. I don't remember how to finish this off. I'm pretty much done here. To derive the contradiction, this is very much like the ones we did last time. You have to imagine when you pump the parse tree there, when we change from UVWXY to UV squared WX squared Y, how does that change the various letters in the string there? Yeah.
So we're supposed to have 3 letters that are going to be the same length N, but when you pump it up,
Yeah, right. In this case, when we change from UVWXY to UV squared WX squared Y, this will change maybe the number of A's and B's, but not the number of C's. It can only change two of them, right? It changes the it changes the V and the X only, right? Which means it's going to change the number of two of them, but not the third. So when we change from UVWXY to UV squared WX squared Y, we increase the number of two letters. Maybe it's the A and the B, or the A and the C, or whatever, but not the third, but not all three. So that means UV squared WX squared Y cannot have the appropriate format, right? It can't use the same exponents where these n's go, right? And that's the problem. So UV squared WX squared Y cannot have the correct format. So UV squared WX squared Y is not in L, and this is the contradiction. Sometimes I write those two little arrows pointing at each other is a symbol for that's a contradiction. Because I already said above that UV squared WX squared Y is in L. All right? This is showing that a language is not context-free. And the proofs, when you do these proofs, they basically all read the same. You just have to, you have to look at the language and make sure that the proof actually works, right, for any particular example that you're looking at. All right, excellent. Let me just say some words. So I'll just say this same proof generally works when we see, can I just say, something like 3 n's on different letters. By 3 n's, I mean they actually have to be the same n. So for instance, the standard example is A to the n, B to the n, C to the n, or something like, I don't know, even if the n's are kind of modified, it doesn't really matter. Something like that. The fact that you see 3 exponents there means that the same proof is basically going to work. When you line up the U, V, W, X, Y, the V and the X would have to be pieces of these 3 parts, right? They would have to come as parts of those in order for when you square them, they still have the same format, all right? What if there's more than 3? Then the same thing still works. If you have something like A to the n, B to the n, C to the n, D to the n, then still the same proof would work. This time you need, the key step is, at the end you say you're increasing the amount of 2 letters but not all 3. And here you would need to increase the amount of all 4, which is certainly not possible. So any of these cases, you will use basically the same proof. I want to talk about one example which is not quite the same, just to give you an idea of how difficult these proofs can be. So when we do, like on the homeworks or on our tests or something, really we're only going to do easy examples, which are like the one that I just did. I consider that to be an easy example. I don't know how easy it is, but relative to other ones, there are some that can be very difficult. So I just wanted to try one example of this is not even a super difficult one, but I will say some require a bit more finesse, maybe I will say. Here's an example which is almost the same. I mean, it looks the same. A to the n, B to the n, A to the n, all right? This is also not context-free. Just the fact that I put an A at the end rather than a C messes up the proof from before, because the proof from before always amounts to, at the end, you say something like, I increase only 2 of the letters, but not all 3 of them. But here, there are only 2 letters. The real issue is that they occur in 3 different places, and so you have to change the proof to indicate that, or to sort of take account for that fact. They appear in 3 different places. So let's see if we can do this one. Just to give you an idea of how sometimes you have to be a bit fancier. So we will begin as before. For the sake of a contradiction, I assume that L is a context-free language. So we get some string u, v, w, x, y in L, and also u, v to the I, w, x to the I, y in L for all I. All right? Now, we can start off the same way. Because we need to maintain this format, a bunch of A's followed by a bunch of B's followed by a bunch of A's again, it is still true that the V and the X are not allowed to mix together the letters, right? The V and the X, they have to be all A's or all B's. So that is still true. Can I just say, as usual, the V and the X cannot have a mixture of letters. So V and X are each all A's or all B's, right? But we can't conclude in the usual way. Like I said, when you change from UVWXY to UV squared, WX squared Y, you are going to increase the number of 2 of the different letters. But actually that might still be okay because in this example we only have 2 different letters. Really the point is that they occur in different places. So we're going to have to do some cases here according to the location where the V and the X are. If the V is the part of the first block of A's or part of the last block of A's, that kind of a thing. So I'm going to do some cases here according to the locations of the V and the X. All right? So, first of all, first case, I'm going to say if V and X are both A's, actually this is an easy case because if they're both A's, then when you increase their powers, you are increasing the number of A's but not increasing the number of B's, and that will break the format. So this is an easy case. If V and X are both A's, then changing from UVWXY to UV squared WX squared Y increases only the number of A's, and so doesn't increase the number of B's, and so UV squared WX squared Y is not in L for the same reasons as we said in all the other examples, because if you're going to make those strings bigger, you have to be increasing the numbers of A's and B's sort of in a balanced way. All right, so that was one case, which we have handled. What about if V and X are both B's? Same thing is true, right? If they're both B's, then when you increase the powers, you are only increasing the number of B's, and that is going to violate the format. So I don't think I want to write all that. I will just say if V and X are both B's, then I'll just say that's a similar case. In that case, when you increase the power, when you pump the tree, you are increasing only the amount of B's, and that will break the format. Because it has to be A to the N, B to the N, A to the N. All right? What if one of them is A's and the other is B's? So there's like 2 options, right? It could be the V is A's and the X is B's, or the V is B's and the X is A's. So if, let's say if V is A's and X is B's, then what? Well, now the locations matter, all right? If V is A's and X is B's, remember U, V, W, X, Y is this format, A to the N, B to the N, A to the N. If the v is made up of a's and the x is made up of b's, it means the v actually is part of the first block of a's because it comes before those other b's. All right, so the v actually lives inside the first block, a to the n, right? The v is part of that first one because it comes before the x, and the x is made up of b's. So the v is part of the first block of a to the n. And now we can say the usual thing. If we increase the powers, then we will be increasing something in the first block of a's, but we will have no corresponding increase in the last block of a's because the increases will happen where the v is and where the x is. So now I will try to say something like that. Changing from uvwxy, when we pump it, to uv squared wx squared y, this increases the first block of a's. That's because of the v, from the v, right? And the block of b's, that's because that's where the x lives, right? X is made up of b's. I wrote block with two c's. I don't know why. This is from the x. It increases the first block of a's and the block of b's, but it has no corresponding increase with the last block of a's, and that's what will break the format. But not the last block of a's. And so that means the overall format will be broken. It can no longer be a to the n, b to the n, a to the n, because you increased the first two parts, but you did not increase the last part. So uv squared wx squared y is not in L, and that's my contradiction. All right? This is almost, so the last case would be if v, like the vice versa from this. If the v is b's and the x is a's, and then that's the same here, only you're talking about the last two blocks rather than the first two blocks. So I'm just going to say a little similarly, this is the final case. If v is b's and x is a's is similar. All right? So, and that's the end of this example. Those are all the cases. All right. This is a bit of a pain to go through this very, very carefully, looking at the locations of each of the possible things. This is what's necessary if you have a more complicated format for your strings. Any questions about that one? Folks at home can ask questions too if you want. Thank you for the chat. I hope you can hear me. All right. I said I had one more example. This one actually is not a hard example, and we're not actually going to go through a proof like this, but I thought it would be interesting. This is sort of a real-world example. Real-world example. By real-world, I mean from the world of real programming languages. Typical programming languages, turns out, are not context-free because of indentation. So if you know Python, Python manages indentation in a way that I'm about to describe. Also Haskell does too. Let me say many real programming languages have meaningful indentation. Many real programming languages have meaningful indentation. What I mean by that is that, like, when you indent stuff, that actually means something in the code. This is true of Python. It's true of Haskell. It's not true, like, in Java. Typically, when you write Java, you indent stuff, but actually, it's not required. You can take out the indents, and it doesn't change the meaning of your code. But anyway, many real programming languages has meaningful indentation, including Python. Has meaningful indentation. You know, you write something with a colon after it, either like a definition or like some kind of a loop, and then everything else you write, all the next lines, they like move over a bit. sort of like there's the bottom level of your code, but then after one of these, you indent a bunch of lines, and then maybe when you're done with this part, you go back to here. The meaning of the indentation is that like all of these guys are considered to be the inside of this thing, whether it be a loop or a if then else or whatever. And then you go back down to the bottom level, right? This is what I mean by meaningful indentation. Grammatically speaking, what you see if you view this thing as a string, like when you write code, usually you would use tabs here to indent, and the tab is kind of invisible, like you don't usually see it. It's just white space. But if I were to write out as a string what this whole code looks like, I'm going to say it looks something like, maybe I have one line at the base level, and then the next level is indented. And then I have a line here, and then another indented line like that, another indented line maybe, and then maybe I go back to the baseline, right? This is how typical blocks of indented stuff, or maybe you could indent, even more than that. Maybe it's like I have some code that's indented 3 levels deep, right? A few lines of that. And then maybe it goes back down to 1 level, right? This is how this kind of thing works. So those big T's represent tabs that you hit with the keyboard, right? But when the interpreter, the compiler, whatever is reading your code, it's going to see these individual tabs, and it has to somehow figure out that these tabs are lined up properly with one another, or maybe they're not, right? And if they are not, then that means something different. Okay, so anyway, what I'm trying to convince you of is a typical correctly indented block of code let's say n levels deep in terms of the indentation, n levels deep. That is to say, like here, I was indenting 3 levels deep here, and then only 2 levels of indentation here. A typical correctly indented block of code, n levels deep. If I ignore the line wrapping, it looks something like this. If I just write, instead of line by line, just write these all one after another as a string, it looks something like that. You have n tabs and then some stuff, and then on the next line, you again have n tabs. It needs to be the same number of tabs in order for the block to be handled properly. So the individual lines would be like, that's the first line, that's the second line, that's the next line, right? But your compiler, it's just going to read your whole file like as a giant string. Anyway, do you believe me? I don't want to go do a proof of this, but do you believe me that any language which has to make checks like this is not going to be context-free? It's because of those repetitions of the n like that, all right? This is just like, something like a to the n, b to the n, c to the n. The fact that you're using more than two n's there. In fact, in a real language like Python, it has to be capable of recognizing any number of blocks, any number of lines inside of an indented block, and has to be capable of keeping track that the indentation levels is the same every time. All right. So the moral of the story is Python, Haskell is another language which has meaningful indentations, I'll just say etc., are not context-free languages because the grammar needs to have some way of recognizing that the indents are balanced properly, and that's not possible to do with a context-free language. All right? Now, I don't know if you recall, it's like a few weeks ago, I actually showed you a grammar for the Python language, and I said, there's a grammar for Python. And that grammar actually was context-free. They're actually sort of playing a little game with you in that description of the grammar. It said something like, there was a line, we even talked about this line specifically in class, I remember. It said something like, indent was one thing, followed by statement, followed by dedent, right? You remember that? I remember the word dedent appeared in class. This is written in the grammar for Python as kind of a cheat. So this indent, truly what this represents is actually a bunch of tabs that are actually interspersed throughout the statement, right? The individual lines of the statement, they all have to have the appropriate number of indents in front of them. And so this line in the alleged Python grammar is kind of disguising the true nature of indents, right? This is how you think of indents, as you indent and then you have a bunch of stuff and then you move back. But when you read the file of code as a giant string, indents don't actually look like that. The indents are actually interspersed throughout the whole statement, and that's what messes it up. So all of that, I just wanted to give a real-world example of non-context-free languages. Languages which have this kinds of indents are automatically not context-free for that reason. All right. Any thoughts about that? Any other questions? This seems like it might be a similar issue if your language has some kind of parentheses balancing, which pretty much any programming language will allow you to put parentheses around things, and you have to make sure that the parentheses are balanced. But actually, parentheses balancing is a much grammatically easier thing to do, and you can do parentheses balancing while still being context-free, although you cannot do indentation balancing. It's strange but true facts. This is how the world is. All right? What do you think? We got 20 minutes? I think that's enough time to start the next. I'll just say a little bit about the next thing. I know it's right before the break. Does that mean that I have this dilemma? Right before the break, do people want to leave early? Or if I let you go 20 minutes early, are you going to say, man, I shouldn't have even gone? Like, I feel like I got to respect you for showing up. Let you stay the whole time. I don't know how you feel about that. I'll just say a few minutes of maybe a little historical background. We won't really get down into the details. But the next major topic, and this will be what we talk about for the rest of the semester, is our last and biggest type of machine. It is called the Turing machine. This is like the granddaddy machine. It's more complicated and more capable than any of the other machines that we've talked about. Although it's a weird sort of historical story that this was also the first one that anybody thought of. Turing thought of this machine before anybody thought of a DFA, which is a lot simpler than a Turing machine. The Turing machine is the most complicated, but it was also the first one. I want to tell you a little bit about the sort of historical context. In the early 1900s, which is the time that Turing was sort of coming up in the world as a young mathematician, axioms had become a big deal. The idea behind mathematical axioms is that you write down hopefully a short list of things which you are just going to assume are true, and then you try to prove everything else based on the axioms. And this was done a very long time ago by Euclid in kind of a revolutionary idea where Euclid wrote down 5 axioms and then tried to prove every theorem in geometry based on his 5 axioms. That point of view kind of went out of style for a long time and then started coming back at the beginning of the 20th century. So what you saw around this time in the 1880s were axioms for group theory. If you take our abstract algebra class, this is what you talk about. Axioms for group theory. A group has 5 properties. This is closely related to axioms for vector spaces, which kind of came later, but the way that we talk about linear algebra these days is based on vector spaces, and they have like 10 axioms or something. There's a big list of vector space axioms, right? In the 1890s, appeared what we now call Hilbert's geometry, which is basically sort of a remix of Euclid's geometry from very, very long ago. Hilbert sort of took Euclid's axioms and cleaned them up a little. Euclid was working, many thousands of years ago, and there were some things that Euclid said which, from a modern point of view, we would recognize as errors, and Hilbert kind of cleaned it all up. Hilbert realized that actually Euclid had 5 axioms. Really, there are more unstated things that Euclid was assuming that Hilbert had to add some extra things. But anyway, and then we had sort of the most ambitious of these programs was Axioms for set theory. And specifically what we now call ZFC, which stands for the Zermelo and Frankel set theory. This nowadays, all of mathematics is done in the context of set theory, sets of things, of functions between sets. But it was not always the case. This really began at the beginning of the 20th century, and there are axioms for set theory. I don't know if you've ever heard about axioms for set theory. Generally, in our, say, discrete math class, we don't try to prove anything based on the set theory axioms because they're kind of complicated and not terribly helpful. But anyway, at this time there were axioms for set theory that were finally demonstrated. And the idea at the beginning of the 20th century, all of math was rewritten in terms of axioms and proofs based on set theory. This is why if you ever try to read very old mathematics, it looks totally different from the way we talk about things now. Even things that, if you understand things like I understand very well, derivatives and integrals. But if you try to read, say, Isaac Newton's writing about derivatives and integrals, it looks totally different, and to me it looks like nonsense, because everything, they had the same ideas, but they talked about them and wrote about them and thought about them in totally different ways. And they had different terminology, like Isaac Newton he didn't say derivative, he said fluxion. They had weird words for everything. So, at this time in history, there was a major question. The major question was, if we make a list of axioms, could there be some kind of mother list of axioms for all of mathematics so that everything in math can be proved using these axioms? Is there a system of axioms from which any theorem could be either proven or disproven? Obviously, this is like the natural goal if you're trying to create mathematics from axioms. Is there a system of axioms from which any theorem could be proven or disproven? And sort of a related question is, given the axioms, is there a procedure which will lead to correct proofs? This is something that, I don't know if you've ever thought about this, but if you have a bunch of axioms and a theorem which you're trying to prove using the axioms, let's say you got 5 axioms. There's only so many ways that you could arrange those axioms together to string them together into a logical proof, right? You use the first axiom and then the second one and then the first one again, maybe. There's only so many ways you could do that. It seemed that maybe you could, in modern terminology, maybe you could program a computer to just create proofs of everything. If all you had was 5 axioms, or maybe even 10 axioms, could you just could there somehow be a procedure for recombining axioms together that would suffice to prove any theorem you could ever imagine? All right? I don't know if you've ever thought about this, especially in the context of mathematics. If there were such a thing, then it would mean people who are trying to do mathematical research by hand should just find something better to do. Why don't you just let a computer prove all the theorems for you, if that's even possible, right? Is there a procedure, though, which will lead to correct proofs for any imaginable theorem? Anyway, this led directly to the question of what is a procedure exactly? Procedure. Nowadays, we say a procedure basically amounts to a computer program or something like that, some kind of very specific description of a process, right? And Turing's answer to this question was that a procedure in this sense is anything that can be performed by a machine. And he specifically said something like my machine. He didn't name the Turing machine after himself. He called it the universal machine. But he imagined that there could be a machine that in theory was capable of doing any computation. At the time, there were computing machines at the time, but they were all special purpose, like one machine which is meant for adding and multiplying numbers or whatever. But they only did what they were built to do. All right. Well, actually, there were other people at this time. I will just mention one of them. Was a guy named Church. This is Alan Turing, and this is Alonzo Church. And Church had a totally different approach, which turns out to be equivalent to Turing's. Why everybody says Turing was the father of computer science, and nobody's heard of Church. People in computer science have heard of Church, but Church's idea was a procedure should be determined or should be defined in terms of any what he called recursive lambda expression. Church's idea was he defined a sort of small family of very, very simple mathematical functions. And then he said, if you allow me these functions, I can turn those simple functions into any computation by recombining these very simple things, which he called lambda expressions. I think Turing's ideas were so influential because they inspired people to actually create real computing machines. There is no such thing as a real lambda expression, and so Church's idea was mathematically good, but didn't really inspire the hearts and minds and the hands of a generation to change the world in the same way that Turing did. So anyway, what we need to talk about is really this right here. My machine. Turing described a very specific type of machine with particular capabilities, and he argued that such a machine could, in theory, be used to carry out any possible computation. Can I just say, the answer to this question here, is there a system of axioms from which any theorem could be proven or disproven? At the time, nobody really had this in their mind, but it turns out that the answer to this question is no. This is why you haven't heard about some sort of master system of axioms for all of mathematics from which everything can be proven. It turns out, actually, there is no such master system of axioms. Even if you decide you're going to work with a certain set of axioms, it turns out automatically there will always be theorems which cannot be proven or disproven using your axioms. This is a deep and puzzling fact which we may talk more about later on. But it was a surprising thing. And Turing actually was part of the work that established this. All right. So that's my history. I think at the beginning, after the break, we should talk specifically about the machine. What exactly is Turing machine's capabilities and how does it work? All right. Thank you for listening to my history lesson for the additional 10 minutes. I'll let you have the rest of the 10 minutes to leave. All right. Don't forget to do the homework. I hope you all have a good break. See you next time. Get your vaccines. It's If you're in Connecticut, you should be eligible.
I gotta figure out what it is in Mass.
Oh, yeah.
Thank you.
All right, see ya.